Hello everyone. Now we continue the course. This moment we were talking about the formation evaluation. In this course we were talking about the mud logging, coring, open hole logging, logging while drilling, and formation test and cased hole logging. So the first we're talking about the formation evaluation. What is the formation evaluation? The formation evaluation, is the process of interpreting a combination of the measurements taken inside a wellbore to detect and quantify oil and gas reservoir in the rock adjacent to the well. The formation evaluation data can be gathering with wireline logging instruments or logging while drilling tools. Study of the physical properties of the rocks and the fluid contained with them. The data are organized and interpreted by depth and represented on a graph called a log. Log is a record of information about the formations through which a well has been drilled. So here is talking about the meaning of the formation evaluation. The formation evaluation is normally from the logging data to analyze the physical properties of the rock and the fluid content of them. This is the main purpose. So why we perform the formation evaluation? Here have the four main purposes. The first is to evaluate hydrocarbons reservoir and predict oil recovery. The second one is to provide the reservoir engineers with the formation's geological and physical parameters necessary for the construction of a fluid flow model of the reservoir. And third one is measurement of in-situ formation fluid pressure and acquisition of formation fluid samples. The number 4 is in petroleum exploration and development. Formation evaluation is used to determine the ability of a borehole to produce petroleum. So we can summarize about the formation evaluation is to find the potential reservoir and predict oil recovery and provides the engineer to the fluid model for production in the future, and also to find the petroleum evaluation to the ability of the potential of the petroleum. So our tools first is the mud logging. The mud logging or well site geology, we call like this, is a well logging process in which drilling mud and drill bit cuttings from the formation are evaluated during drilling and their properties recorded on a strips chart as a visual analytical tools and stratified across sectional inspection of the well. So here have some kind. First is cutting fluid and record, analyze, and to make the stratified across the section, and provide continuous record of the penetration rate, lithology, and hydrocarbon shields. This information supports wireline logging data from the cuttings and oil strains or odor of the oil may be detected and become an excellent quantity indicator. And fluorescent lamp is also a great help in detecting the oil shields. So mud logging is during the drilling time, use the cutting and anything retained to the surface and the mud logging caper, the logger, to take the visual and make the analyze for the for the formation information. And mud logging is the gas. If have the gas record and the lithologic sample are plotted along with surface parameters such as the rate of the penetrations and weight on bit and rotation per minute on the mud log, which serve as a tool for the drilling engineer and mud engineer. And some problems. A discrepancy between the time of the rock was drilled and the time it reached to surface, particularly for deep wells, which it take 2 or more hours to reach to the surface. Yeah, we can call this the lag time. The second tool is the coring. Coring is one way to get more detailed samples of a formation is by coring, which formation sample is drilled out by millions of the special bits. This sample can provide detailed lithologic description and porosity, permeability, fluid saturation, and grain density. These parameters are measured in the laboratory and serve as a basis for the calibrating the response of the porosity logging tools and to establish a porosity permeability relationship. So it's a very radical information. Two techniques commonly used at present. The first is the whole core. A cylinder of the rock, usually about 3 inch to 4 inch in diameter and up to 50 feet, is almost 15 meters to 60 meters, 80 meters long. It's cut with a core barrel, a whole pipe tipped with a ring-shaped diamond and a shape-studded bit that can cut a plug and bring it to surface. Taking it full core is an expensive operation that usually stops or slow drilling operation and can be done only before the drilling has been done. The cheaper technique for obtaining sample of the formation is side wall coring. In this method, a steel cylinder, a coring gun, has whole position steel bolted mounted along its side and mold the gun by short steel cable. The coring gun is lowered to the bottom of the interval of interest, and the buttons are fired individually and the core will be retrieved. Advantage of this technique are low cost and the ability to sample the formation after it has been drilled. And core preservation. Once the core is retrieved to surface, then it's important that it should remain as unchanged as possible. The core should be prevented from drying out, coming into contact with oxygen, or being mechanically damaged. The core barrel is filled with resin to prevent the core from moving and to minimize the exposed surface area. Freezing the core in freezer container. The core sample is wrapped in a plastic film and also aluminum foil and deep in the mounting wax. The core analysis can be divided in two categories. The first is conventional core analysis. The other is special core analysis. For the conventional core analysis, the core is usually labeled, cut lengthwise to make the structure visible, and provides information on lithology, residual fluid saturation, ambient porosities, ambient gas permeability, and grain density. And the special core analysis provides the following information: porosity and permeability at evaluated confined stress, electric properties such as formation factor and resistive index, and capillary pressure, and webbability and relative permeability, and mechanical rock properties such as compressibility and water fluid sensitive for injective and wear performance. So for the core analysis can provide a lot of the information. And next one tool is open hole logging. Open hole logging, also known as wear logging, in the practice of making a detailed record, a wear log, of the geological formation penetrated by a bone hole. Open hole logs are run before oil or gas well is lined with pipe or cases. And the principle of wear logging. A wear log is a record of certain formation data, visual depths. The appropriate downhole logging tools instrument called sounder, about 3.5 inch in diameters, is lowered into mud-filled hole on logging cable. These tools will measure the electrical consistency and radioactive properties of the formation. The result will be analyzed to determine which of the layers are pervious and permeable and likely to contain hydrocarbon. A depth calibration will record the length of the cable in the hole. So this is the wear logging, the gamma ray. Survey is normally done from the bottom up, as the sounder is pulled out of the hole and continuous measurement signal is sent to the surface where the data is processed and recorded as a recovery. And the last one is the electric log, developed by Conrad and Marco Schellenberger, who found Schellenberger Limited, and introduced to USA in 1923. It can be divided into two main types. The first is a measurement of lateral electric current in rock, it's SP log, and another one is measurement of induced electric current, the resistivity log and induction log. So the first one is spontaneous potential log. This type of the log is known as self-potential log. And the spontaneous potential log record weak electric current that flow naturally in the rock next to the wear bone, the lateral electrical. And the log shows the boundary and thickness of each layer of the rock, especially permeability, sandstone, and the impermeable, like the shell. And because of the spontaneous potential log is so simple to obtain and provide such basic information, it's the most common log. This is the spontaneous, this is higher is the shallow, and this is the sandstone and also shallow sandstone. We can say the difference, the spontaneous potential, And used for detecting the permeable beds and its thickness, and locating their boundary and permeable correlation of such beds, and determine formation water restrictiveness, and also quantity indication of the bed shallowness. The next one, the second one, is resistivity log. The resistivity log used to measure the resistivity of the formation and thus the possibility of the hydrocarbon shoots. A sounder sends an electric signal through the formation and relays it back to the receiver at the surface, inducts electricity. The surface detector will measure the formation's resistance to the current. A rock which contains an oil or gas saturation will have a higher resistivity than the same rock completely saturated with the formation water. So the third one is induction knock. This knock is used to measure the conductivity of the formation and thus a possibility of the hydrocarbon shoes. A rock which contains an oil or gas saturation will have a lower conductivity than the same rock completely saturated with the formation water. Induction knock use an electric coil in the sounder to generate an alternating current loop in the formation by induction. Induction tools give best result when mode resistivity is high with respect to formation resistivities. Fresh mode or non-conductive fluid in oil-based mud which is non-conductive. Induction knock is only option availability. The number 4 is the dielectric knock. Its response is essential to water and is unaffected by the presence of the hydrocarbons, particularly important in determining the irreducible water saturation when oil-based mud are used. And also the nuclear lock. Just as sponsored potential resistive lock record natural and induced electric current, nuclear lock, also called radioactivity lock, record natural and induct radioactivity. 3 types of knock: the gamma ray knock, a natural knock, and formation density lock. The gamma ray knock record a natural gamma radioactivity of rock surrounding the bone hole. The gamma radiation arises from 3 elements present in the rocks: isotopes of the pulsatile uranium and thorium, used for the defined shell base because of KUT are largely concentrated in associated with the clay minerals. It's used to define permeability bands when spontaneous potential knock cannot be employed. For example, when RMF equals water. The second one is electron lock. It's too orbiting a electron lock. A sounder sends automatic particle called electrons through the formation. When the electrons collide with hydrogen, the hydrogen shoots them down. The response of the device is primarily a function of the hydrogen molecular concentration. When the detector records no neutron, it means a lot of the hydrogen is present, many compounds of water and hydrocarbon, but a lot of rock. Consider as a pre-porosity lock because hydrogen is mostly present in poor fluid, the water, hydrocarbons. The count rate can be converted to the apparent porosities. The third one is formation density lock. This device measures the number of the protein, then be related to electric density of the formation. Electron density is related to apparent bulk density, which equivalent to formation bark density. Is use able to detect the formation lithology, like the solid or acoustic knock. It can provide continuous record of the time taken in microsecond foot by sound wave to travel from the transmitter to the receiver of the sounder. The velocity of sound through a given formation is a function of its lithology and porosity. Density. No porosity rock are characterized by high velocity of sound wave, and vice versa for previous or less and less density formation. The next one is logging wire draining. Logging wire draining is one of the major drawbacks of the wireline information is that it receives several hours to several weeks after the borehole is drilled. During this time, the formation can undergo significant alteration, especially in its fluid saturation, effective porosities, and relative permeability. Logging wire draining allows wireline type information to be available as near as real time as possible. The logging wire draining is a technique of converting wire logging tools into the wire-borne downhole as part of the bottom hole assembly. The logging wire draining, some available measurements in logging wire draining technique like the gamma ray, resistivity, density, lateral, solid, formation pressure, formation fluid sample, the borehole caliper, like the ultrasonic, azimuthal caliper, and density caliper. And next one is the formation test. Its meaning of obtain formation once concerned the liquid and pressure in an open hole formation. Here have three methods: wireline testing, draining steam test, and wire test analyze. So for the wireline test provides reservoir fluid samples, reservoir pressure, and indication of fluid mobility and information on reservoir continuity. Two types. The first is repeat formation tester, we call RFT, and formation interval tester, we call FIT. The RFT is run into the hole and a continuous digital readout of the hydrostatic pressure is obtained. At any point in the hole, the tool may be actuated to force a rubber pad against the wall of the hole, and the tube in the center of the pad is forced hard against the formation. The formation fluid will flow to chapter through the tube. The wireline test and also the formation interval test is used for singular tests, only one pressure rate and one fluid sample for each run. If the tool actuated, a pad is tightly against the formation to form a seal against hydrostatic pressure of the fluid in the hole, and a shaped charge is then fired into the formation, opening a passageway of the formation fluid to follow into the chamber in the tool. At the same time, the formation pressure will be recorded. And the draining steam test. A drill steam test is a procedure for isolation and testing the surrounding geologic formation through the drill steam. The test is measurement of the pressure behavior at the drill steam and is a valuable way to obtain important sampling information on the formation fluid and to establish a probability of the commercial production. Their test is made by lowering a var, a packer, and a length of perforated tailpipe to level of the formation. The packer set against the wall of the bunghole so that it seals off the test interval from the mud content above. And also the var is then opened and the formation fluid will follow to the surface through the drill pipe. The amount of the fluid produced will represent the fluid production can be expected from the well. And also the next is well test analysis. Two types of the testing: pressure build up and drawdown test. The primary objective of the well testing are to establish it. The first, the permeability thickness and the permeability. The second is stratification by sequence testing of the layer, and well productive, and investigate reservoir boundary and size. The amount of the fluid procedured well presents the fluid production can be expected from the well. And also is the cased hole logging. Two major errors of the cased hole logging is the production logging and the reservoir monitoring. The production logging refers to obtaining production or injection profile over a completed interval. The reservoir monitoring refers to obtaining a real-time information about changes in hydrocarbon situation, crucial for understanding water contact movement. And other surface include cementing bond log, which is used to evaluate the degree of isolation provided by casing cement. So here we have a video about the mud logging and coring and the casing hole operation. Have a video introductions.
You will learn about mud logging and how it provides early indications of the presence of reservoir rock and possible hydrocarbon accumulations. Mud log data is acquired while drilling and not only provides petrophysical data, but also provides drilling data that results in a more safe and optimal well construction. The following mud logging topics are covered: the process of mud logging, including hydrocarbon shows and lithology determination, the components of the drilling mud system and where cuttings samples and gas samples are collected, and identification of lithology and hydrocarbon types from mud log data. The coring section provides an introduction to cutting cores in the well during the drilling phase. You will learn about the basics of taking cores, the different types of cores, and the special equipment required. The following coring topics are covered: why cores are justified and who needs core data, which type of core is most suitable based on data requirements and budget, and the advantages and disadvantages of each of the three types of cores. The cased hole logging section provides an introduction to cased hole logging used in cased holes. The following topics are covered: common cased hole logs and how the data are used, two types of pulsed neutron logs and how they can be used for reservoir monitoring, and the basic sensors on the production logging tool, PLT, and why it is run.
And next one, introduce about the well logging.
Millions of dollars can be spent drilling an oil or gas well, so it is very important to gather as much information as possible at every stage to determine if it makes good business sense to continue drilling and complete the well. Logging a well is one very effective way oil and gas companies gather detailed information about the different layers of rock they've drilled through. This gives greater certainty about whether or not hydrocarbons are present. If the well is not promising, the process can be stopped and the well abandoned before incurring the large costs of completing the well. Once the well has been drilled to its target depth, the drill pipe and bit are removed from the hole. A specialized logging crew and equipment are brought on location. The crew assembles a probe, which is several different logging tools connected together. Depending on the number of tools in the assembly, the probe may be 70 to 120 feet in length. Using diverse scientific techniques, each tool performs a different kind of measurement of the rock and fluid properties within the geological formations surrounding the wellbore. The probe is lowered down into the wellbore on a wire line until the top of the probe is below the target depth. The process is carefully monitored by the well logging crew and geologists. As the probe is raised back up the hole, the various logging tools are activated by computers on the surface that produce a graph called a well log, which represents the geologic properties of the layers below the surface. On the well log, the gamma ray tool measures any radiation emitted by the rocks. Rock with lower amounts of radiation is called cleaner rock, such as limestone and sandstone. These are more likely to contain hydrocarbons than dirty rock. Notice that near the top of the log, the line is relatively flat and the reading is consistently high, indicating dirty rock, likely shale. But near the bottom, the reading fluctuates because the logging tool is entering a sandy area which has little radiation and could contain oil or gas. This data is called the apparent water resistivity curve. It indicates the potential for water in the rock formations surrounding the wellbore. At the top of the log, the line is at the left, which indicates more than likely the formation is wet or shaly. As we move down the log, the measurements change drastically. This indicates a quickly changing mixture of shale or other water-bearing formations on the left, to sand with the possible presence of hydrocarbons as the curve moves to the right. This next reading, called the spontaneous potential curve, shows geologists when the instrument passes from one rock formation to the next. The spontaneous potential tool uses two sensors, one at the surface and one down the hole, to compare the natural electrical charges at the surface with the underground rock. Some layers of rock have a positive charge compared to the surface, while others have a negative charge. A shift to the right on the log indicates a positive charge, usually associated with shale. A shift to the left indicates a negative difference, usually associated with sandstone. The center section of the log shows readings from the resistivity tool. The overlapping lines are 6 resistivity curves, each one measuring at a different distance from the wellbore how well the rock conducts electricity. The left side of the grid shows less resistance to electricity, while the right side denotes greater resistance. Oil or gas-bearing rocks are less conductive and therefore more resistive to electrical currents. Notice that for most of the vertical distance, the rock has less resistivity. This is likely shale. The higher resistance is likely an indicator of sand, a layer that can hold hydrocarbons. The reading from the neutron porosity tool, which can count how many hydrogen atoms are in the surrounding rock, can be seen in this section of the log. A higher concentration of hydrogen indicates the possible presence of oil. When the curve moves to the right, this indicates fewer hydrogen atoms. So as we move down the wellbore, we can see that the amount of hydrogen is generally decreasing. This means there is either very tight rock that cannot hold oil, or gas may be present. Working in tandem with the neutron porosity tool is the density porosity tool. It measures the space between the electrons in the rock, also known as bulk density. Near the top of the log, there is a greater amount of density, but as we move down the wellbore, the log indicates that the rock is becoming less dense. You'll notice that in this section, the density porosity curve and the neutron porosity curve cross over. This is significant. Whereas the neutron curve indicates either tight rock or gas, the density porosity curve tells us that the rock is more porous and therefore cannot be tight rock. This area indicates the high probability of natural gas. The next curve represents the measurements taken by the sonic tool. It shoots sound waves into the formation and records the time they take to return. Dense rock will have a faster travel time, while porous rock will be slower. Finally, on the left edge of this section, we see the reading from the caliper tool, which measures variations in the size of the wellbore. These variations can affect the accuracy of the other tools on the probe. So based on this measurement, the computer recalibrates the readings from the other tools as necessary. These are the most common logging tools used by oil and gas companies to gather information about the rocks and any fluid or gas content thousands of feet below the surface. There are numerous other tools designed for specific logging situations. The more complicated the geology is, the more diverse the set of logging tools needs to be. None of these tools by themselves can provide sufficient information to make an informed assessment about the well. But combined, these tools offer a more comprehensive and reliable perspective. When trained geologists look at well logs such as this, there is enough information for them to literally envision what the subsurface looks like. Because most wells are logged, oil and gas companies can research these logs to evaluate prospective drilling sites. When a company plans to drill in a new area, they can look at the logs of nearby wells called control wells. Lining up the logs, adjusting for variations in the surface altitude of each well, the geologist can get a good idea of the rock structure and possible presence of hydrocarbons across the area. This information is very helpful before drilling begins. With this information, oil and gas companies can drill new wells with greater confidence and promise of success.
Okay. For this chapter, yes, it's already introduced about the mud logging and coring and open hole logging, and logging while drilling, and formation tests and K-score logging. And also, yeah, we make the videos to some video introduce the mud log about function, how to do that, and coring about procedure, and also the open hole logging and the wireline logging introduce different types of the log in the tools. So I think from this course we can get information how to perform the formation evaluation, more relying on the log, and also talking about the formation tests, different types like the FIT, RFT, and DST, and also the other type of the tests. All of these tools and methodology need to evaluation the formation, including the permeability and porosities and rock, and also the formation is very important for our reservoir engineer, and also the geological engineer can make the evaluation. Okay, we continue our course. In this chapter, we were talking about the well completion and the simulation. And in this course, we will talk about what is well completion, and setting protection casing, install the tubing, installing the Christmas tree, and the type of the wear completion, and the factor influencing wear completion selection, and type of fluid, completion and walkover fluid, and preparation and wear stimulation. So where is wear completion? And after careful interpretation and consideration on wear test data, the calling, the logging, and a decision is made whether to set production casing and complete the wear or to plug and abandon it. And second, a decision to abandon is made when the wear is not capable to produce oil or gas in commercial quantities. However, sometimes wells that were plugged and abandoned at one time in the past may be reopened and produced if the price of oil or gas have become more favorable. And then the completing a well means install equipment in the well to allow a safe and controlled flow of petroleum from the well, and a series of activities to prepare an oil well or a gas well so that the well can be flowed in a controlled manner. All wells have to be complete. In addition to the casing that lines the wellbone, recall the chapter 4, tubing and a system of fluid valves must be installed and cannot operate alone, must join effort with other sub-disciplines such as production engineering and reservoir engineering. The second is setting production casing. Setting the production casing is the final casing in the well. The hole is drilled beyond the production interval, and production casing is set and cemented through the pay zone. The casing and cementing actually seal off the production zones. That means setting production casing. And this is the well structures. We can say first we drill, and first is we install the conductor pipe, and then we drill the first, and then install the surface casing, and then drill the intermediate zone and install intermediate casing, and then to the production casing, and drill the pay zone preparation. It's like this, setting the production casing, and then install the tubing. Tubing is run into the well, smaller diameters compared to production casing, and the remover to sever us away for oil or gas to follow the surface. And the packer is attached to it just near the bottom. Packer is placed at the depth just above the production interval. When the packer is expanded, it grips the wall of the production casing and forms a seal between outside of the tubing and the inside casing. And then install the Christmas tree. A connection of valves called a Christmas tree is installed on the surface at the top of the casing hanger. As the well production flows up the tubing, it enters the Christmas tree, so the production can be controlled by opening or closing valves on the Christmas tree. So the Christmas tree is a control system and type of the completion. The first is open hole completion. Open hole completion, it means production casing to be set above the zone of the interest. So this is the This is the open zone, the production zone, but the production casing will be set on the top, above of the placing zone, and here with the tubing and the packer. So from the pump, anything to arrange, ensure the fluid and oil from the tubing to the surface. And second type is liner completion. The liner completion means a liner is installed across the pay zone, and it can be divided into two: the screen liner and the perforate liner. The screen liner, it means casing is set above the production zone, and an uncemented screen and liner assembly is installed across the pay zone. This is one of the type of the liner completion. This is the pay zone, and from here is use the screen and the liner system, and at the packer of the production casing and the tubing inside to the packer to seal the tubing and the casing, and then the oil and the petroleum fluid come from the tubing to the surface. And the perforate liner completion is casing is set above the production zone, and a liner assembly is installed across the pay zone and cemented in place. The liner is then perforated selective for the production. So it's like this. This is the production casing at above of the pay zone, and then set the packer in the production casing and the tubing to here. In the production zone is running the liner and make the perforation to bring the oil and the gas from the perforation here and use the pump to the surface. And perforation casing completion is similar like liner. In production casing is cemented through the pay zone, and the pay section is selective to perforate. And tubing nest or reduced diameter completion, it means the production tubing is cemented and perforated for the production. And the factors influence wear completion section. The first is natural occurrence of the field. For example, does it have a big reservoir to justify development, and the potential of oil production and the planning of the territory recovery. For example, do we need any artificial lift in the future? And the limitation with the operation of the field. For example, is the oil field located at a remote areas? And type of the flue. There have three types of flue, namely casing flue, tubing and annular flue, and tubing flue. Casing flue, it means large flue rate. Low tubing is required, used in Middle East. And the tubing and annular flue is large flow rate and flow segregation. And the tubing flue is used widely, especially in Malaysia, due to the safety, may use one tubing string or more. Our future discussion will be based on the tubing flue only in a perforated casing hole completion. And singular tubing completion. Singular tubing sequentially completions is the simplest way of completing the well. It's this method where it's completed for single zone with single tubing. And single stream commingle completion. All the reservoir available in a well are produced simulating nearest through single the screen. Should be avoided if possible to animated cross-flow phenomenon. Monitoring of reservoir performance is strictly difficult. Single-stream selective zone completion permits selected production, injection, testing, simulation, and isolation of various zones. Selectivity after completion is accomplished by opening and closing sliding swivel between the packers. And multilateral completion. In this completion, multiple branches are drilled from a single hole. It's used to improve productivity from closely spaced target zones. And completion and walkover fluid. It's a fluid that plays against the production formation while conducting operations such as well cleaning, clean out, hardware replacement, and gravel packing. Walkover fluid is used when a walkover job is done on a well. In this discussion, it refers to the same completion fluid. Walkover fluid doesn't include well stimulation fluid, fraction fluid, cementing slurries. So the packer fluid is placed above the topmost packer. Avoid use water-based mud as packer fluid. Must be chemically stable. Acceptable upper limit corrosive is 5 meters per year. If possible, at about 1 mile per year. Two major criteria must be met by packer fluid. It's limited setting of the solid and provide protection for corrosion or embrittlement. And perforation. Since the per zone is sealed off by production casing and cement, perforation must be made in order for oil and gas to flow into the well bone. Hole made in the casing, cementing, and formation through which formation fluids enter a well bone. Usually several perforations are made at a time. And perforation incorporated shape change explosive, which created a jet of high pressure, high velocity liquid and jet perforation. It can be overbalanced or underbalanced perforation, and well line covering perforation or tubing covariate perforation. The two types of the perforation. Perforation gun is lowered into the hole at the depth where the oil and gas formation is found. We can see the photo A. And after the gun is lined up properly, powerful explosive charges are fired from the control panels at the surface. This explosive blasts a hole in the steel casing and cement and up several feet out of the rock here. And finally, the oil and the gas fluid flow into the holes and up well to the surface. It's a photo C. And perforation fluid is a fluid that plays against the production formation during perforation. It's ideally fluid with no solids. And fluids to be considered: salt water, clean water pose no problem. When overbalanced, may push charged debris into the formation. Acetic acid excellent perforation fluid under most conditions. The presence of H2S may magnify corrosion problem. And nitrogen used for in low pressure formation or when associated with high rate time or sweeping cause, and when a special test requires formation to be free for contamination. And the wellhead assembly. Comprise Christmas tree, casing head, and tubing head, wear head is referred to casing head and tubing head. Christmas tree is installed on top of the wear head. The tubing head is located above the casing head. And the wear stimulation. Sometimes petroleum exists in a preparation but is unable to flow readily into the wear because the formation have very low permeability. The lateral flow permeability formation. The formation damaged around the wear bone caused by invasion of the preparation fluid and charged debris. Excision or fraction is a method used to increase the permeability near the wear bone. Excision if the formation is composed of rock that dissolved upon being contacted by acid, such as limestone or dolomite, then a technique known as excision may be required. Excision operation basically consists of pumping from 50 to thousands of the gallons of acid down the wells. The acid travels down the tubing, entering the preparation, and contacts the formation. Continue pumping force the acid into the formation where it produces channels. The channels will provide a way for the formation's oil and gas to enter in the well through the preparations. The most common exit system in use are hydrochloric acid. This is the most widely used acid in treatments, with concentration range between 7.5% and 28%. The most common is 15%. It will dissolve calcium carbonate, dolomite, siderite, or iron oxide. The mode acid. This is a mixture of HCl and HF hydrocarbon acid, and is generally 12% HCl and 3% HF. It will dissolve clay materials in the formation, along with feldspars of color. The hydrofluoric acid will react with La, K, C, and C in the clays to form insoluble precipitates, so it's advisable to avoid always pre-flush with HCl. Second type is organic acid. These are actic and formatic acid. They are slower acting than HCl and are generally used in high temperature wells and wells with high alloy tubing to reduce corrosion rate. And ADTA. This is ethylene diamine terrific actic acid. It dissolves carbonates and sulfates by chelating them. It's more expensive than the other acids and the reaction is slower. Fracturing is a proper process to increase the permeability of reservoir rocks, for example the sandstone, by pumping a special blend fluid down the well and into the formation under great pressure. Pumping continues until the downhole pressure exceeding fracture pressure of rocks. Formation literally cracks open, with opening between 0.25 to 0.25 inch. Meanwhile, sand or aluminum pellets are mixed into the friction fluid. These materials are called propellant. The propellant enters the fractures in the formation, and where pumping stops and pressure decreases, the propellant remains in the fractures. Fracturing. Since the fractures try to close back together after pressure on the wear is released, the propellant is needed to hold fractures open. This proper open fractures is permeable enough to provide passage for oil or gas to flow into wear. So this is talking about the wear complexions. So later I will show some videos to introduce about them.
Once the surface section of the well is drilled, the drill pipe is pulled out of the hole in order to lay the casing. This is done for environmental reasons to hydraulically seal the formation layers containing aquifers from the flowing hydrocarbons later on, once the well is completed. The casing string is made of numerous joints of the same size screwed together at the collar. The casing pipe is selected according to its outer diameter, its wall thickness, its length, its weight by unit length, and the grade of steel it is made of. The selection of grade of casing depends on several variables, including the size of the hole, the rugosity of the drilled hole, the expected pressure of the flowing hydrocarbons, the H2S content, as well as the economic considerations. Once the entire weight of the casing string is solely suspended by the hangers, the casing is considered laid in place. In order to secure the laid casing string to the formation, cement is pumped through the casing shoe at the bottom of the well, letting the cement flow between the casing and the formation. To allow further operations in the well, the cement requires sufficient curing time. Once the cement has dried, the seal of the aquifers would be established. The drilling then continues through the wiper plug, the casing shoe, and the cement at the bottom of the hole until the desired depth is reached. This is called total depth, or TD, and is where the pay zone is anticipated. To evaluate the presence and economic feasibility of this pay zone, the drill pipe could be equipped with logging while drilling tools to evaluate the formation while drilling. It is a common practice to lower wireline logging tools to evaluate the formation and determine the economic feasibility of the drilled well. This is done by logging the anticipated pay zone through various types of sensors to determine the key properties of the zone. After the pay zone has been determined and deemed feasible, the wall needs to be prepared to extract the discovered hydrocarbons. This process is known as the completion of a well. A common completion method requires inserting a casing string into the newly drilled open hole to prevent the borehole wall from caving prematurely during the various steps of completion. To allow further operations in the well, the cement requires sufficient curing time. The cementing process is not always a flawless operation, and the resulting cementing job might contain some bonding issues that would undermine the strength and integrity of the casing, especially during perforation. The bond of this cement with the formation and with the casing is evaluated using a cement evaluation wireline tool. This tool determines whether the cement job is optimal. If not, further remedial operations are required. To establish a path with the hydrocarbons stored in the pay zone, a perforating gun is now lowered to the target depth. Wireline is the preferred conveyance method for short and light gun strings. To deploy long and heavy gun strings, a technique referred to as tubing conveyed perforating, or TCP, is required. Using sensors part of the gun string, the guns can be accurately positioned in front of the targeted reservoir. The charges in the gun are now ready to be ignited using the surface perforating control equipment. Once the correct depth has been confirmed, the gun is fired. The charges in the gun explode, providing a path through the formation, the cement, and the casing to the production tubing. The perforating gun is then pulled out of the hole. Now, the weld is perforated and the path has been established between the stored hydrocarbons and the weld bore. While the drilling rig is still in place, production tests are performed to confirm the commercial viability of the reservoir before the production string is installed in the well. A typical production string is made of a tubing string that includes a packer near the bottom end. The production packer is installed above the top of the perforations to ensure that the flowing hydrocarbons reach the surface only through the production tubing. Before the drilling rig is dismantled and moved away to its next location, the wellhead equipment, commonly referred to as the Christmas tree, is installed on top of the well. With the well completed, the production of hydrocarbons can begin. These hydrocarbons will fill storage tanks or feed pipelines until the day when the production rate has diminished and the well is plugged and finally abandoned.
Now, here I have a video talk about the type of the well completion, the liner, singular, dual, and multiple.
Liner completion is a type of well completion in which the production casing is lowered, cemented, and subsequently perforated into the pay zone to allow the flow of fluids from the pay zone into the wellbore. A liner completion may use either a production casing or a production liner. This technique is necessary when incompetent formations, which are likely to collapse, are present. Single tubing completion is a well completion method in which a small diameter production tubing is run to the top of the pay zone in the well. Dual tubing completion is a well completion method in which two sets of production tubing are run parallel to each other to the bottom of the well. This technique is used when two zones are produced simultaneously. The space between the tubings and the annulus is sealed off with two sets of packers. The upper zone is sealed both above and below with the help of these packers. This ensures that fluid from each zone is diverted through its own tubing and that each tubing carries fluid only from one zone. Multiple zone completion is a method of completion used when the well has penetrated two or more pay zones that lie one below the other. The tubing strings are suspended side by side in the production casing string, each having a different length with respect to the pay zone from which it would produce. Each tubing is packed off to prevent the mixing of reservoir fluids from different horizons.
Okay, now we have a summary about these chapters, well completion and simulation. In this content, we talking about what is the well completion and the process, setting production casing, and install the tubing, install the Christmas tree, and talking about the type of the well completion and factor influencing well completion selection, and type of the fluid and completion and walkover fluid, and different types of the perforations, and also for the different of the well simulation like the fracture, accident, and others. So for this, it's also very important about the workover. And now we get into the next chapter. It's about the production. All the wells, just like the before, we from the exploration and formation, revelation and draining and completion. Now we start to the production. In these chapters, we're talking about the introduction of the production and the flowing wells and artificial lifting, engineering and oil treatment and storage and sale of oil, and also the salt water disposals. So now we first is introduction about the production. The production stage is the most important stage of a well life when the oil and the gas are produced. And by this time, the oil rig used to drill and completion the well have moved off the whalebone, and the top is usually outfitted with connection of valves called Christmas tree or production tree. And these valves regulated pressure and control flow and allow access to the whalebone in case further completion work is needed. And from the outlet valve of the production tree, the flow can be connected to a distribution network of pipelines and tanks to supply the products to refineries, natural gas compressor station, or oil export terminal. So, and also, as long as the pressure in the reservoir remains high enough, the Christmas tree and production tree is all that is required to produce the well. And if the pressure depletes and is considered economic variables, an artificial lift method can be employed. So we can say this is the finish the completion, and this is the reservoir. From reservoir, this is whalebone, this is the tubing, this is Christmas tree with wellheads. All of these finishes, we can produce. We produce the fluid and to the separate, use the valve to the separator. Separators always have the three types of fluid: the gas and the gas outline to gas, and also the water to the water treatment, and the oil to sear. This is very simply to introduce the production process. So this is the typical crude oil production chain. The oil, the red line, we can say the production internet is the oil, the production fluid from the inlet to the separators. The separators at the top of this is the gas outline from air to outlet, and then the middle of this is about the oil to the oil outline. Sometimes the oil and the water, sometimes together, the water to water line, and then the water to the water treatment also have some gas from the gas outline to the gas. Sometimes is the flare, and also sometimes to recovery, and also here have some the water from here to water outline, and then to the separate to the hydro water treatment, and then the oil to here is to the hydrator, and the one stage desalter water to water line to here to circulation to return again. and oil from this line to water from this line and to others, and gas from here to here, and then scanning the exchanger again to dilution water pumpment to from here, and then second stage desetter, and finally with the cyclement to here. This is very typical of the crude oil production. The second part we were talking about the flowing wells, and define as anywhere which has sufficient pressure in the reservoir to cause the oil and gas to flow naturally to the surface through the wellbone. This is one type. A well which produces oil and gas without any means of the artificial lift. This requires relatively little equipment and expense to bring the oil to the surface. The equipment commonly used consists of the tubing, wellhead, and Christmas tree. We can see this photo. This is the pay zone, oil and gas from the perforation from these channels and from the tubing from the tubing to the surface. This is the Christmas tree. Use the Christmas tree to the chalk to the protection equipment, and then to here to the surface treatment. This is one type of the flowing wells. And artificial lift. The artificial lift is a technique used to bring oil from the reservoir to the surface because of the decreased reservoir pressure. So generally this is achieved by use of the mechanical device inside of the well, known as pump or vessel string, or by decreasing the weight of the hydrostatic column by injection gas into the liquid some distance down the well. The artificial lift is needed in the well when there is insufficient pressure in the reservoir to lift the produced fluid to the surface. It's also often used naturally flowing well, which do not technically needed to increase the flow rate above what would flow naturally. The artificial lift. There are currently 4 common methods of artificial lift. The first is beam pump. The second is submersible pump, and gas lift, and hydraulic pump. First is the beam pump. This pump is designed to be inserted inside of the tubing of a well, and its main purpose is to gather fluid from the beneath it and lift them to the surface. The most important components are the barrels, valves, trapping and fix and position. The pump is connected to the pumping unit at the surface by a string of sucker rods. The sucker rods are strokes up and down in the tubing, activates the pump at the bottom. At the surface, a large mechanical device called the beam pump unit is attached. This is a very typical beam pump. So we can see from this is the surface, beam surface, and this is downhole equipment. From here we can see this is the engine or motor. Sometimes use electric, and here is the gearing reducer, and here is the crank arm, and here is the counterweight, and here is the pitman arm, and here is working beam, and here is the hose head, and then connect the bladder, and then press the polish rod, and then the starting box, and then connect the sucker rod and in the tube and in the tubing and in the casing, and then use the pump here. So sometimes it's the surface from the hose head up and down to connect the socket rod, and with the pump with this string up and down to make the oil and gas from here to up to the surface. This is the beam pump. Depending on the size of the pump, it generally produces 5 to 40 liters of liquid at each stroke. Often this is an emulsion of crude oil and water. The pump size is also determined by the depth and the weight of the oil to remove, with deeper extra requiring more power to move the heavier length of the sucker rod. The advantage of the beam pump, first, is high system efficiency. Second, it's economical to repair and service, and more flexible, and adjust the production throughout stroke, length, and speed, and high storage value of the surface unit to downhole equipment. So the disadvantage of the beam pump is limited to relatively low production volume and less than 1,000 barrels per day, and limited to the onshore application is the big surface unit required. So the second type is the submersible pump. We call it the ESP. ESP consists of an electric motor attached to a pump on the end of the tubing string. The electric motor turns a 30 and centrifugal pump which forces oil from the bottom of the well up through the inside of the tubing and out at the surface. And the electricity is supplied through an electric cable attached to the side of the tubing and connect to the electric motor. This is one type of the ESP. ESP uses the electric cable to the tubing, and the pump is here, and electric motor is in the pump. From the electric motor to force motor electric turns a centrifugal pump which forces the oil at the bottom of the well to the tubing and then to the surface. So the advantage of the ESP is high volume and depth capacities and high efficiency, often over 1,000 barrels per day, and no maintenance and minimal surface equipment required, and high resistance to corrosive downhole environment, and used in deviated well and vertical well with doglegs. The disadvantage of the ESP is poor ability to pump sand. And next one is the gas lift. It's a series of devices called gas lift valves are inserted into the sides of the tubing. The gas is injected into the well through a tubing casing annulus and enters the tubing through the gas lift mantlets and gas lifting valves. The fluid in the tubing is made lighter by gas, and the gas, as a result, its mixture is pushed to the surface by reservoir pressure. A source of the gas and the compression equipment is required for gas lifting. The proper installation and compatibility of the gas liquid equipment, the surface, and in the whalebone are essential to any gas lift system. The advantage of the gas lift. The gas lift is an artificial lift process that closely resembles of the lateral flow process and basically operates as an enhancement or extension of that process. The only major requirement is a available and economic supply of the pressure gas. So the disadvantage of the gas lifts is not feasible if no source of the gas present. Its high initial capital pressure cost and maintenance intensive and difficult to operate. So another one is hydraulic pumping. We call it jet pump. It's a high pressure oil. It's pumped into the well through the tubing string. At the bottom of the well, the powered oil enters a mechanical device, causing it to reciprocate. This mechanical device activates a pump, which lifts the oil from the producing formation together with expanded power oil to the surface. The systems consist of a surface power fluid system, a primary mover, a surface pump, and a downhole jet pump. So this type is like this. This is the photo, yeah. With the jet pump can pump the oil to the surface, the tube. The power fluid from surface actuates the engine, which is in turn drives the pump, and the power fluid returns to the surface with the produced oil. The advantage of the hydraulic pump is no moving parts and also high volume capacities, and also the multiple well production from a single package, and no pump maintenance. The disadvantage of the hydraulic pumps is high initial capital cost and complex to operate. So this is the different types of the artificial pump. Later, I will show some videos of the different types of the pumps.
From the power unit rotates the crankshaft. One complete rotation of the crankshaft is called a stroke. When the beam moves the sucker rod upward, it's called an upstroke. And when the sucker rod is moved downward, the movement is called a downstroke. So, as the crankshaft rotates, the beam seesaws up and down. Okay, let's look at what the beam pumping unit is doing. On the upstroke, the beam lifts, in essence, two different quantities of weight. The weight of the sucker rods and the weight of the fluid being pumped up and out. On the downstroke, the only weight on the beam is the weight of the sucker rod string itself. These pieces of information, the weight of the sucker rod string and the weight of the fluid being removed, are important to consider when a pumping unit is sized for an application. To counterbalance the weight of the sucker rod string, we use a counterbalancing system, in this case a physical weight, that is somewhat less than the weight of the sucker rod string. The power produced by the power source must be transmitted from the source to the gearbox. This is accomplished by using belts. One or more belts move around sheaves or pulleys mounted on the prime mover and gearbox shafts. Since the speed of the prime mover is much faster than is needed to move the sucker rod string up and down, speed reduction is necessary. Different sized sheaves reduce the speed of the prime mover. The smaller sheave is mounted on the prime mover, and the larger sheave is mounted on the gearbox shaft. Depending on the particular ratio of sizes, The smaller shiv will make about 20 rotations for each rotation of the larger. V-belts are used because they have a greater contact area than flat belts. The friction developed by this greater contact area provides better power transmission from shiv to shiv. But to maintain this efficiently, the belt must be adjusted to its proper tension. Also, for safety, the belts and shivs should always be covered by a guard. If the guard is removed, the moving belt and shivs can cause serious injury. Finally, efficient operation of the beam pumping units relies upon proper lubrication of the critical moving parts. The saddle bearing and equalizer bearing carry the heaviest part of the load and usually have to be lubricated with bearing grease. The gears in the gearbox are lubricated by oil splashed from the bottom of the box. However, care must be taken to keep water out of the oil so that the gears don't corrode. The wrist pin bearings come with sealed grease reservoirs and easy access grease fittings.
And lastly, talk about the jet pump, the hydraulic pump. The jet pump is one type of the hydraulic pump. Now we continue. Just now we have the video to introduce the 4 types of the artificial lifting the pumps. Now we continue to talk about next stage about the oil treating. Generally, what comes out of the well is mixture of oil, water, gas, and even sand. The foreign materials such as water and sand must be separated from the oil and gas before they can be sold. This process is known as oil treating or oil dehydration, in which water is removed from oil. The amount of these foreign materials is referred to as the basic sediment and water. Normally, the basic sediment and water content must be less than 1% before the oil will be accepted from sale. Basic type of equipment used for oil treatment are separator, free water, clog out, and heater treater. So we talk about the separator. The separator is a large pressure vessel designed to separate production fluid into their constituent compounds of oil, gas, and water. The separator utilizes the force of gravity to separate oil-gas mixture due to different density of the fluid. The oil, which is heavier than the gas, falls to bottom of the vessel and taken off through the fluid line. The lighter gas rises to the top and is removed for separate sale. So the major compounds of separator: the primary separation device or section, the secondary graphite certain, the separating section, means extra to remove small liquid particle from the gas, and then the gas outlet, and the liquid setting, separating section to remove gas, and the liquid outlet. So here have the separation inside of the separator. Initial separating the section A, the gas will be from the gas line, from the top of the gas, and section B is gravity setting, and section C is mixed extra section C, and then the liquid sum for the section D from the oil. So clarification of the separator. The clarification by operating configuration is a horizontal separator, may vary in size from 10 or 20 inch in diameter and 4 to 5 feet seams to seams, up to 15 to 16 feet in diameter and 6 to 60 seams to seams, and manufactured with Módulo tubing or dual tubing shell. For the vertical separator, it varies in size from 10 or 12 inch in diameter and 4 to 5 feet seam to seam, up to 10 to 12 feet in diameter and 15 to 15 feet seam to seam. And self-regular separator is usually viable 24 or 30 inch up to 66 to 72 inch in diameters. So the function of the separator, the two-phase separator, gas is separate from the liquid with the gas, and the liquid being discharged separately. So the three-phase separator, in three-phase separators, where fluid is separated into gas, oil, and water, with three fluids being discharged separately. So the molar tubing horizontal separator is like the typical horizontal separator. So here is inert and inert dividing. So the gas-liquid interface from here, liquid connection section, and grave setting section, and mixture extractor. So here the pressure control. The top of this is the gas from this pressure control valve and to the gas out. Liquid from this and from the lever control from liquid out. This is the two-phase. And the double tubing horizontal separators is like this. It is the inner divider and from the gravitating setting section, and gas from here out, and then here is from the flow line to double the liquid connection section, and then liquid from the liquid control valve to the liquid out. And vertical separator. Vertical separator is more for the density, oil and gas mixture. For the gas up to the outlet of the gas, and with here is the floating and oil from oil control valves from oil. And also this is the inside of this. And the spherical separator is a little different. So insert from the top of this tank and the grave starting the gas liquid interface and the liquid, this is the interface. In the divider is the first and the mix extra, and then from here the gas from here to the liquid from here, liquid out, and the gas from this side to the top bottom of this, the gas out. So this is talk about different kind of separator. Later, I will make introduce some video to introduce the separator.
Separators in one form or another are the most used vessel in the energy industry. Scrubbers, knockouts, treaters, drip pots, and gun barrels are all forms of separators. In this chapter, we will introduce you to two types, horizontal and vertical emulsion separators. Separation happens in many ways and for a variety of reasons. Think about why you separate what you recycle from the trash. It's helping a process that's going to take place later. It boils down to the fact that there are advantages to separating things. The same is true in the energy industry. Resources come to the surface in many forms and combinations. Separation adds value to the resources. Sometimes we separate components for safety reasons. Nature helps us in the separation process. Often, the differences in specific gravity of a resource are all that is needed to facilitate separation. Nature helps us in the separation process. Often, the differences in specific gravity of a resource are all that is needed to facilitate separation, but they need enough time and a steady state to do so. Retention time is a big factor in the separation process. Retention is the amount of time that a fluid stays in the separator. With enough retention, the different specific gravities will settle or separate from the emulsion. You can see in this example, over time the fluids separate as they move from the inlet side to the outlet. Some other outside influences that are needed to achieve separation are mechanical devices such as diverter plates, wave breakers, mist extractors, and weirs. All three sectors of the energy industry incorporate separation in their processes. Initial separation occurs in the upstream sector. As the resources are moved through the midstream sector and the conditions that they are exposed to change, there is a need to further separate the product. Separation is needed in the downstream sector to achieve the final product before it goes to the consumer. This short list shows the most common places you will find chemistry products controlling the separation process. Separation takes place when the makeup of a well stream is not meeting the customer's requirements. There are guidelines to help producers decide the extent of separation needed. We will discuss these guidelines in more detail in Level 2 separation. Here are a few pictures of common styles of separators. The customer's needs determine what type of vessel that the equipment manufacturers make. The size, working pressure, separation capabilities, accessibility to the internals, and whether it's horizontal or vertical could all be factors that determine how a separator gets built. Phases will be discussed multiple times in these chapters. Two-phase simply means that we are separating gas from liquids. Three-phase means that we go a step further and separate gas from oil and oil from water. It all goes back to the customer's requirements. Separators can be high or low pressure. Anything under 500 psi is considered low pressure, and anything above 500 psi is considered high pressure. Chemray provides different options for the controls on these vessels for both high pressure and low pressure. There are times that you have to look closely to see the differences between high and low pressure vessels. One confusing factor is that high pressure controls are sometimes needed on low pressure vessels in order to have proper control. High pressure controls can work well on low pressure vessels. However, low pressure controls do not work well on high pressure vessels. We define mechanical controls as any device that uses levers and linkages to operate. Pneumatic controls use some form of gas to operate and control. These gases can be natural gas produced from the well or air supplied by an outside source like a compressor. There are other gases used in our industry for supply, but these are the most common. Here we see the different combinations of chemray controls used in different applications. If the operating pressure is low enough, mechanical controls are a great choice. Some regulatory agencies tightly control fugitive gas emissions. Mechanical valves don't use gas to operate and therefore don't emit gas under normal operation. Enclosed buildings usually found in colder climates may not allow pneumatic controls to be used for safety reasons. The quantity and quality of gas is important when choosing pneumatic controls. The process may also dictate when pneumatics are required. For example, metering fluids usually requires pneumatic controls to maintain a level of accuracy because they can be opened and closed quickly. Please familiarize yourself with the basic connections of this vessel. Thank you.
Okay, just now we from the video to have the general introduce about different types of the separators. So next we talk about the free work lockout. The free water lockout used to separate oil, water, and gas. This mixture flow into the vessel through an inert valve and then are allowed to slow down in the larger setting chamber. Any free water mixed with oil settles to the bottom. Oil is removed through a separate line, and gas which rises to the top is extracted through the third line. In principle, free water lockout is almost identical to separator. This vessel is called a free water lockout because it's designed to animate only free water, not water which has been emulsion phased. The free water lockout, it means the oil and water outletters. The oil and water outletters are controlled by never controlled valves. Here is the water control valve and letter and oil control valve from the outlet, and also the water and from the water valves, which prevents the vessel from drying completely and keep the gas trapped in the top of the vessel, and commonly used for low pressure wells and can be used to handle high volume of fluid. And vertical free water knockout is similar if this is from the low pressure wells. Use the valves, and from the IP separators from here, and then from the free water lockouts. So like this, the gas from here and from the FR and PC, and then to the compressor, the gas to compressor, and then from here to the bulk treatment, and then the water from here to the water skimmer. The next one we introduce about the heater treater. Also, the heater treater is also called emulsion treater, used to separate oil and water emulsions. Is similar to free water lockout, but the treater has heating capacity with the inclusion of fire tubings. The combustion of the gas, oil and gas within the fire tubing is used to heat oil and water emulsion. And this is the fuel gas with the fire tubing here, and the inert with oil, water, and gas in the top, and clean due to the heat. The oil, the clean water is in here, and the water in the top of here, and oil is top here, and here is the juncture, and the gas from the gas valve and the gas outline to here, and oil from the oil control valve to the clean water, and water from here to clean water, and this to return to emulsion again. A heat treater, as the oil and water mixture grow hotter, the emulsion breaks and forms into clean oil and clean water. The water is removed from the bottom and sent to the water disposal system. The clean oil is drawn off the center of the vessel and sent to the oil storage tank for sale. Any natural gas in the oil-water emulsion exits at the top of the heater treater. So the combinations Typical compilations of equipment is shown below. It's the surface vicinity of typical oil. This is the well, and oil, water, and gas. And use the free water lockout. The gas is up, water is below, and then emulsion. An emulsion, and with the heater, and the gas out, clean oil to storage, and water to the water disposal system. The remaining oil and water emulsion levels leaves the free water lockout and is transferred to the heater and treater. On an offshore platform, a high-pressure separator often will be used instead of the free water lockout. So this is the same very typical surface vicinity of oil wells. The well to free water lockout, the gas to the gas line, and then to the heater for emulsion, and then oil to storage, gas to gas line, and water to the water disposal treatment. So the typical oil treating facility. This is the incoming production stream to the gas separator. The gas will to the gas compressor, and then to the free water lockout. The top of the water gas will to the gas outline, and then the water is to the water trade skimmer to the water trade system, and then go to the heater treater, and gas to the gas outline, and the oil clean water to the oil storage tank to the, and maybe to from, and also from pipeline to the pipeline and quality to sale, or maybe in the storage user truck, and water to the skimming tanker, and oil emulsion for reprocess and return to here, and the clean water to the source end, and clean water to injection pump. This is a very typical oil treatment facility. So for the oil storage and sales is onshore. A typical facility, sufficient storage is provided to accommodate oil from 2 to 3 days of the production. Oil may be withdrawn from tank and sold by trucks or tanker or through pipeline to the refinery, and this automatic costly transfer measures the volume of oil as it passes into the pipeline. It also measures the gas and water content. This is clean water from the treater heater and to the oil storage tank, and then by truck to sale, and by the pipeline to sale, and maybe from the pipeline and also the storage tank like this to the refinery. This is onshore. In the offshore storage or sale, offshore production platforms can sometimes be equipped with oil storage equipment if the platform is located in shallow water. The clean oil can be sold through the pipeline extending from the platform along with the sea flow to the land. This is the wells, and the wells with this is offshore. This is the wells from the oil process equipment and in the storage, and from the pipeline to the oil sale. So in deep water operation, oil is shipped through a pipeline along the sea floor to another storage platform in shallow water. And sometimes storage platform is not necessary and the oil is shipped directly into the cell line. For remote oil fields, deep water locations and small oil fields where seabed pipelines are not cost effective, so they use the FPSO in a good option. Oil is stored in the FPSO and will be offloaded onto tank. So because of the offshore, the platform is small, so they need some like FPSO to storage oil and then offload on the tank or to sail. Last is the water disposal. And to prevent environmental pollution, the water produced must be injection to the ground, often into the same rock from which it is drawn. The water is taken from the oil processing equipment and usually sent to a storage tank until sufficient volume has been accumulated. Often in offshore operation, the salt water from the wells can be disposed of into the sea itself. However, the water must first be sent through several cleaning devices which remove any trace of the oil. This is the offshore. For the onland, the water sometimes is in the injection, sometimes is to sell to the third party, sometimes to the river or to the plant, any different ways. So the gas trading, the natural gas consists of various compounds which are present in different concentration, the water and the impurities. Reason for trading is to meet sale specification and customers' requirements, and to recover other materials such as CO2 and elemental sulfur from H2S at higher price if market separates, and to facilitate transmission to prevent hydrorate formation. So the gas sweetening process. Gas sweetening is the most common gas treatment process. As long as amine gas treating and excess gas removal, the process consists of two main units: is absorber and regenerator. In the absorber, amine solution absorbs H2S and CO2 from the upflowing soil gas to produce a sweetened gas stream, for example, a H2S-free gas, and as a product and amine solution rich in the absorbed excess gas. The resultant rich amine is then rotated into the regenerator, a stripper with a reboiner to produce regenerated or lean amine that is recycled for reuse in the absorber. So the gas sweetening process. The sweet gas normally goes on to additional processes such as dehydrogen and dihydrocarbon recovery. The excess gas contains most of the CO2 and sulfur compounds is either flared or sent to the cloud source recovery unit. So this is the different type of the gas. The carbon 1 to carbon 4, the nickel 2, H2S, a CO2, and COS is carbon insulfate, and CHS is carbon disulfide, and DSR. All this, we call this sour gas. Sour gas to sweat residue gas is to C1 to C4 and N2 and N2, and then to the exit gas H2S, CO2, COS, CS2, RSR, and H2. And this exit gas contains and to flare or send to the cloud source recoveries. So this is the gas sweating process. The gas sweating process is just now talking like this. Make up water, the sour is the sour gas to the bottom trace and absorber, and the top trace is to gas sweat, and then the rich amine is into the lean. It's into the rich amine is into the legs absorber is the top tray and bottom tray, but the bottom tray is liquid, and the top tray is condenser, and then to the reflux drum, the exit gas is from here, and then return to the pump and reflex to the regenerator again, and regenerator again. And the liquid for the reboiler, the vapor inside the regeneration and others condensate. And here is the lean line pumped back to the absorber again. So the typical operating rate, the absorbers is 35 to 50 degree and 5 to 250 atm absolute pressure, and the regenerator is more higher the temperature and more higher about the pressures. So this is the gas sweating process. And next I will introduce some of the videos to introduce the process. Okay, now we go into the last chapter. As a petroleum engineer, all of us should know the HSE management. It's very important to the petroleum engineering. So in this course, we have the contents of the followed. The first is HSE in oil and gas industry. The second is importance of HSE in oil and gas operation. The third one is the key components of HSE in oil and gas. And the fourth is the challenge and risk in HSE for oil and gas. And number 5 is best practice in HSE management. And number 6 is HSE innovation in oil and gas. And last one is the future of HSE in oil and gas. So first we talk about the HSE in oil and gas industry. We all know that the oil and gas industry is by its nature a high-risk industry to health, safety, and environment. It's because the industry's products, oil, and gas, and others, like hydrocarbons produced and transported and supplied to the world market with a substantial amount of the fuel and raw product for a number of the industry activities. So therefore, the oil and gas industry handles large quantity of flexible and hazardous substances in the high energy environment in content subsurface and with high pressure and temperature scenarios. In some cases, the risk situation is complicated by a high toxic gas oxide byproducts like hydrogen sulfide. So this part is talking about introduce about our HSE in oil and gas industry. It means during we have a lot of the activities is high risk, and also our products like the hydrocarbons is like toxic and flexible and others, and also a lot of activities. So it means that HSE in the oil and industry is very one of the most important because of the high risk activities and high risk environment and high toxic about the substance. So this is introduced HSE in our industry. And also, when we know about this, and we should know about the others. So as the definition adopted by the joint ILO WHO Committee on the Occupational Health from 1950, the occupational health is adapting of work to man and of each man to his job. It has the following contents: the promotion and maintenance of the highest degree of the physical, mental, and social well-being of workers in all occupations. So it focuses on prevention among workers of the departures from healthy caused by condition at the workplace, and to protect the worker in their employ from risk and hazards that would result into advised healthy condition, and also to the placing and maintenance of a worker in an occupational healthy environment. So this is the very general introduce about the HSE in oil and gas industry. So the next one we talk about the importance of the HSE in oil industry. So in the revenue of the oil and gas, HSE isn't merely a regulatory requirement. Of course, the regulation requirement is very important, is the compliance from the legal requirement. And it's also a moral and ethical responsibility. So the sector's operation often involving high-risk activities, including drilling, exploration, extraction, transportation, and refine. All of these high risk. Each phase brings both inherent hazards necessary robust HSE protocols. This is one important. And also the HSE standards for healthy, safety, and environment in oil and gas industry. It refers to the practice, protocols, and regulation implemented to ensure the well-being of the workers, protect the environment, and prevent accident or incident in the exploration, draining, refine, and transportation of the oil and gas. And also the HS measures encompass various aspects like risk assessment, safety training, emergency response planning, environmental impact assessments, and compliance with industry standards and governmental regulation to minimize potential hazards and promote a safer work environment. So this is have several talking about because of our HSE is not only for the regulation requirement but also for the moral and aesthetic responsibility. This is one thing. The second thing is because we have a lot of the high-risk activities, and also we have a lot of the in-kind hazards. This is the second one. The third one, for the HSE standards, is to ensure HSE healthy, safety, and environment, and also is should, according to the legal requirements and government requirement, to ensure our people activities. And others, we have a lot of the HSE tools to ensure, to promote a very safer work environment. And also for the HSE are crucial components in the oil industry due to high-risk leisure operation, from drilling to transportation. Each phase poses unique challenge that can lead catastrophic consequence if not managed properly. So we can divide several healthy risks. The workers in the oil industry are exposed to various health risks, including exposure to hazardous chemicals, extreme temperatures, and physical injury. And also the short-lived exposure can lead to long-term health issues, such as respiratory problems and skin diseases. Second one is about the safety concerns. The safety is a paramount concern in the oil industry. The accident such as explosive fires and oil spills can result in significant loss of life and property. For instance, the Deepwater Horizon disaster in 2020 resulted in 11 fatalities and extensive environment damage. And also we can consider about the environment impact. The environment impact of oil operation is profound. The oil spills, the gas flaring, and the waste disposal can lead to several ecological damage, like the Exxon weather oil spill in 1989 is a stark reminder of the long-term environment consequence of the integrated HSE practice. So we can conclude the importance of HSE. The first is high-risk environment from drilling operation and flexible gases. The second one is the regulation pressures, even the local and international laws. And third one is the cost of incident like fatality, fine, and reputation will have big costs to spend on it. And also is the public expectation and social license to operate to ensure it. And also HSE the competitive and incentive advantage for the company development. So that is very important of the HSE in oil industry. So when we know about this, we should know the key HSE components. The first, from the healthy aspects in the industry, the oil and the gas workers are exposed to the various healthy risks. Just now we're already talking from the exposure to hazard chemical to economic strains, and priority employee healthy through regular medical check-ups and economic assessments, and wellness program is a fundamental. So the second part, the safety protocols and measures. The safety remains a top priority, encompassing strengthened protocols for equipment handling and emergency response plan, and regular safety audit, implementing a culture of safety consciousness is vital to prevent accident and mitigate risk. And also the third one is thinking about environmental consideration. The industry impact on environment is substantial, and embracing sustainable practice, reduce carbon footprint, and implement techniques for minimizing environment impact are pivotal components of HSE strategy. And also in Colombia, for the oil and industry and the gas industry, very important is according to the environment license. Not only exploration but also the production license. All the environmental license have a lot of requirement about like the water, air, and also the animals, and also the soil. All this should be monitoring, should follow the environmental license and make the compliance, and every year should receive the annual visit to check out the inspection. So this is the responsibility for the company to follow the environmental license requirement to ensure the environment management. And also here it's about how to control the safety. Here have some very critical HSE components. The first is risk assessment tools. Why we should have this? For the safety, is very important for the risk assessment, risk control, and risk monitoring. So we should have the risk assessment tools like hazards and JSA, and also the NOPA. Use these tools, we can, according to the activity, according to the process, and according to the technique, to identify the risk before the job. And we find the risk with the different levels and make the different control measures to ensure we can control the risk. And the second one is the safety management system. The safety management system is also the most important. This is the HSE management tools. Mostly it's the local requirement, also the international requirement. Very famous is the ISO 45001 and OSAS 18001. This is for the safety management system, and also for the environment management system, the ISO 1401, and severe prevention, and others. This part of the environment program is should according to the environment license and make the environment management plan and policy, and also the manual and the procedures and forms. The another tools is occupational healthy program or system is about like the noisy, physical, and economical should according to the occupation regulation to make the action plan. Except this, it's also very important is training and competency. Yeah, to make the like the safety induction and certification, and a lot of training on the how to use the tools, how to make the identification, and how to identify the hazards, and how to the operation. All this is the training program. We can, according to the position, to make the training metrics and make the training plan, and then implement it and ensure the people can be improved. And another one is emergency response. The emergency response is also one of the most important. Once have the incident, we can use the emergency plan and to reduce the result of the incident. The different activities yet have different plan. Very popular is about the fire drills and oil severe response. And next one is about risk monitoring and reporting. Like the incident, anything we should very according to the regulation to report and monitoring the KPI and report incident and make the analyze. And also one is very important about is the contractor HSE management, because in the oil industry most of the job is by the contractor. So the contractor management is also the very important, like the training, also the HSE campaign, and also the monitor their performance. So this is give some examples about the HSE key components. The next one we will talk about HSE challenge in oil and gas. Of course, oil and gas have a lot of challenges and risk. The first one is the workplace hazards. The oil and gas sector face numerous hazards, from the machinery-related accident to exposure to the toxic substance. And also we have an example in high temperature, high pressure, rotary activities, and mechanic activities, and machinery activity, work and heat, and also the confined space and operation, and also like electric and fire, explosive, and toxic, and many risks. So how to mitigate this risk requires continuous risk assessment and protective measures. So this is the working place hazards. The second one is about regulation complexity. And we all know that of the development of the industry, the regulation is more and more strictly, and the navigation through the divided global regulation added complexity HSE management. So the compliance with various standards while maintaining operational efficiency remains our challenges. And third one, technical advancement and impact on HSE. While the technical enhance operation efficiency, it also introduced new risks. For example, like the scent control. The scent control new technique. When the new technique, any new technique can bring the new risk, and also the new energy cars also can bring the new risk. So embracing innovation like automation and AI demands a carefully balance between the productive and safety. And the third one is inherent hazards. Inherent like the high pressure and high temperature and confined space, and also the offshore and remote location. This is also high challenge and also the weathers. And also it's about aging infrastructure, the facility equipment as the old, without the automatic, it also can bring the hazard and risk to our operation. And third one is culturally diversity in global teams. In those moments, a lot of the country, even in Colombia, have a lot of the international oil company, international the service company. So the culture in different country has also bring the challenge to the HSE management. And also the human error and the behavior factors, in the like especially in the field, the people sometimes forget something. The people sometimes with the wrong PPE, and sometimes the people is not the correct operation procedures, and all of this can bring the human error. So the human error and directly to injury or bring the risk to the people's life. So these factors is very important. And also the climate risk and the natural disaster. In this moment in all of the world, especially this year in Colombia, the earthquake, and also the heavy raining, in different areas, and also the flood, and also landscape can also bring the high rate to the operation. So, based on the challenge, here introduce some HSE best practice. This practice can support for the HSE management. The first one is the leadership, commitment, and safety culture. The management of the leadership is one of the most important, because the highest of the leadership behavior is know the standard of the employee. So the managers and the leaders should visible leadership to the employee. Let the employee to know the managers very focused on HSE to really ensure the HSE is the priority. Only by this it can influence the employee behavior to establish the good safety culture. The second one is the behavior-based safety program. It's talking about the human error. The BBS is very focused on the people's behaviors. They come from the 5S or 5S or 6S to improve the people's behaviors by observation and by the human error control, such like the campaign, like the safety is first. I can control the risk, and I can control the human error, like this campaign, to improve the people's behavior and awareness. And third one is about the KPI, and establish the leading KPI and lagging KPI, and also monitoring it, such as the TRIR and L2IF, and also the near miss. Because of this performance is a good tool to analyze its trends, to find the root cause, and give you alert to make the corrective action plan to avoid in the future have the similar incident and keep on the good performance. And number 4 is regular audit and inspection. So audit and inspection is very important. From the audit, we can according to the audit plan, maybe from the management system, and maybe from your yearly plan, you go to the field to review, like the role and responsibility, like how to make the risk assessment, the PTW, the GSA, and also the hazard funding closure. By this inspection, you can find what's the problem about the management now, and what's the opportunity, and provide suggestion, make the improved plan in it, and then implement it. It can be a good chance and a good tools. And next one is the root cause analysis of the incident. Incident should be the very good lesson learned material for the improvement. Each incident we should according to the different tools to find the root cause. Yeah, it's from technical, or it's from the control measures, and from the PPE, and from the plan, and from the supervision, to find the management issues and technical issues, and find the root cause and behind of the incident. Only according to this, you can improve your management system and management tools. And next one is the toolbox talks and project meeting. This talk about the communication. The communication is very important. Only before the working, before the operation, you make the fully risk assessment and find risk, and make the control measures, and make the socialization and training to all the people who join in the activities. And by this way, it's a very good chance, very good tools to avoid accident. And the digital permit to work system. Let's talk about PTW. The PTW is most important, the risk control tools. Yeah, it's digital, yet from the review by different levels, we can divide the job for different levels, and control by different levels, and follow the permit to work procedures, and follow the control measures. And next one is learning from incident across site. It means here have very good practice with one company. Every week they have a weekly meeting, and they find across site the incident, and make reflection, and find the root cause, and compare with their own management, and from the incident find the improvement opportunity. By this way, it's very good tools. And also the transparency and reporting. This is also very important. All the HSE management process should be recorded and report. And by this way, this data, this information is a good tools for your internal interview or audit, and analyze to find the trends and make the improvement action plan. And I think all of this is just an example for the HSE best practice, and also like the life saving rules, and also like the golden rules, and also like others, the good practice, and also the benchmarking from other companies and other the good practice to learn from there to improve. And here is talking about HSE innovation in oil and gas. The first is drillers for inspection, like flare stacks and pipeline. It's from technical. And second one is wearables for healthy and vertical monitoring. This is for the healthy. And third one is virtual reality training. The virtual reality training can bring the people in the real field, to improve their training feeling, to improve their training effective and result. And also the LOT sensor for gas, pressure, temperature. This is for technical. For technical improve to use the safety incision to ensure the equipment, to ensure alert and first time to find the dangerous substance, and also use the AI for predict risk analysis. This is from the technical side, and also the digital twins for the scenario testing. This is also the testing is online to more effectivity and more practice and more useful. This is some HSE innovation in the oil and gas industry. And also we think about the future of HSE. In the future, not only focus on the HSE but also for the sustainability goals. It's integrating with ESG and sustainability goals. This is one of the future. The second one is the zero emission technical, the low carbon energy. It's about environment. This is the new energy, and also the new technical. And third one is public HSE performance disclosure to socializations. And also the next one is remote monitoring and automation to improve the essential, to reduce the people employed to face the dangerous substance and dangerous process and dangerous activities, to improve the management, and also emphasize on mental health and well-being. It also to control the human error, to improve the people's awareness. This is the future of the HSE industry. So just now, this chapter is talking about the petroleum engineering HSE meant. So after that, I have some questions to let you know. The first one, what role does HSE play in oil and gas industry? From this class, we can see that the HSE ensures the safety of workers. This is the one, to safety to life. The second is protect the environment. The third one is mitigate risk inherent in oil and gas operation. The total of this part is protect the safety, environment, and also the priority, and to reduce the operation risk. This is the first question. The second question is how can company improve HSE practice? Just now I talked about several HSE practice like the leadership, and like the BBS, and also like the emergency training. So you can conclusion is by fostering a strong safety culture, and investing in employees training, from the training to improve the awareness, improve the capacity, and improve the skills, and also embracing innovative technical for the risk management. This is the second question to thinking. The third one is why HSE compliance crucial in the oil and gas sector. Yeah, it's essential. It's ensure operation continues. This is for the operational and prevent accident. This is the result, and preserve the environment. Thus, safeguarding the company's reputation. And number 4 is what are some emerging trends in HSE and oil and gas. He's talking about in the future. What about HSE in the future? So it is the technical advancements and sustainability initiatives and the shift towards renewable energy source. So the last question, how does HSE contribute to the industry long-term sustainability? This is also talking about the important in the future and now. Yeah, it's by balance operational efficiency with environment responsibility, ensure a safer workplace, and embracing innovative and sustainable practice. So this part we talk about the HSE management. We can make the conclusion is that so the HSE in oil industry is very important because we have a lot of the risk operation, high risk operation, and high risk substance, and also according to the law, we should protect our safety, environment, and also the people's life. The second part is talking about the importance of the HSE in oil industry, and also talking about the key HSE component is about healthy, safety, environment, and also the leadership, and also the BBS and others, and also talking about the HSE best practice like the strong culture, leadership, training, emergency, and also talking about the HSE the future. How about the HSE future, and how about the HSE contribution to the company? All of this is very important. Okay, so everyone, all these course already almost finished. Yeah, we can have a general summary here. In this course, we talking about how about the oil, how about the petroleum, how about what's the petroleum engineer, about their functions, and how the oil come from, and talking about the rock and information, and also how evaluate the fluid, and also talking about the exploration and geologic and geophysics, and talking about this, and how we what the purpose of the exploration, like the seismic, relative, and negative, and also talking about the draining operation, from the draining operation, the draining different draining rig, and the draining tools, and the draining process, and then we talking about the formation evaluation, the different tools for formation evaluation, the different logging, how about the logging working, also the how to identify the fluid and find the oil potential, and then we talking about the completion and simulation. How about what's the different type of the well completion, and what's about the different simulation, the fracturing and exceeding and others. And then we talk about the production, how about the production procedures, and what's the artificial lifting systems, and also the how about the producing phase, and about the refined the oil treatment. And then we talk about the last one, we talk about the HSE management, also in petroleum. And so in this class, here I make a very general conclusion. As we conduct this fundamental generally through the petroleum engineer, we have explored how oil forms deep benefits the earth, how we evaluate the rocks that hold it, and how we discover exploration and draining, transportation, completion, and production, and to bring it to surface. And also we have seen how formation evaluation guide our decision, and how production strategy optimize recovery, and how every step from exploration to extraction is shaped by science, engineering, and innovation. But most important, we have emphasized that none of this can be sustained without a strong commitment to healthy, safety, and environment. In an industry that operates in complex and often challenging environments, and HSE is not just a responsibility, it's a core value that protects people, community, and also the planet. So the petroleum engineer is more than a technical field. It's a vital force powering the world and shaping our energy future as you continue your studies and careers. Carry forward not just the knowledge, but the mindset of safety, sustainability, and continuous learning. So I hope from this course can make a general introduce the fundamental of the petroleum engineering. So finally, from this class, you can learn the basic information. So I hope every one of you can enjoy the petroleum engineer the journey in the future. If you have any question, you can directly call me. Thanks. Bye bye.